Hey there, 6th grade. The topic of this video is going to be exponents and square roots, and so we're going to start by defining some math terminology that deals with exponents, and then we'll move on to using square roots. The majority of the things you see in this video should be review for you from 5th grade or before, but you may learn something new as well. So the important thing is to make sure you take good notes. Make sure you write down anything that I write on the screen. It should go on your paper, and then you can also write more than what I write on the screen. Feel free to jot down anything you hear me say, or maybe even write down questions over things that come up in your mind as we're doing a problem or as I'm talking about a topic. Feel free to write that down as well. So we're going to start out in the top part of the notes here. I'm filling in some of these blanks. And so it says exponents are a convenient way of writing repeated multiplication. That's what we use exponents for in math classes when we want to write repeated multiplication. And there are three different math terms you might hear when we're dealing with exponents. The first term is base. So the base is the number that is being multiplied when we're dealing with exponents. So if we look down at this problem here, I have the multiplication problem 10 times 10 times 10. So 10 repeated 3 times, okay? So this is repeated multiplication. So I can rewrite it using exponents, and 10 in this case is the base, okay? Because it is the number that is being multiplied. The other part is the exponent, and the exponent tells how many times the base is being multiplied by itself. So down here again, 10 is being multiplied by itself 3 times, and so we use this 3 kind of above the 10 in the upper right corner, a small 3, to represent that 3 times multiplication, and the 3 is called the exponent. When you put the base and the exponent together, we have what is called a power. And so the whole thing is read as 10 to the third power. Okay, 10 to the third power means 10 times itself 3 times. So in the first couple of examples down here, we're just going to take each of these multiplication problems and we're going to rewrite them using exponents. So in the first problem, we have 7 times 7 times 7 times 7 times 7 times 7. So we know that 7 is going to be our base, since it's the number that's being multiplied by itself. And if you count the number of 7s, it's being multiplied by itself 1, 2, 3, 4, 5, 6 times. So this would be 7 to the 6th power. Number 2, we're multiplying 9 by itself. So 9 is our base. And we're multiplying it by itself 1, 2, 3, 4, 5, 6, 7, 8 times. So this would be 9 to the 8th power. Okay, moving on to 3 and 4. Now I'm going to give you a power for each of these, and we're going to rewrite it first as repeated multiplication, and then we're actually going to come up with what number that multiplication would give you. So number 3, this is read as, again, 2 to the 4th power. 2 to the 4th power, and 2 to the 4th power means 2 times itself 4 times. 2 times 2 times 2 times 2. So that's the repeated multiplication part. The second part of the directions say evaluate, and that just means, okay, we'll simplify that. Okay, tell me what 2 times 2 times 2 times 2 actually is. Well, we know 2 times 2 is 4, so I can replace this 2 times 2 here with a 4. I also have a 2 times 2 here, and I know this 2 times this 2 is also 4. And everything here is being multiplied together, so really I can rewrite this as 4 times 4. 4 times 4, if we know our multiplication facts, we should get 16. So that tells us that 2 to the 4th power is actually equal to 16. Number 4, we have 10 to the 6th power. So that's going to be 10 times itself 6 times. So we'll rewrite it as repeated multiplication first. And then I'll do the same thing. 10 times 10 is 100. And then I have two more pairs of 10s. I have this 10 times this 10, which is also 100. And this 10 times this 10, which is also 100. Now, if you know the trick for multiplying by 10s or by 100s, you know that you can just count the number of zeros. So 10 times 10, there are two zeros involved in that multiplication problem. That gives you a 100, which also has two zeros. 100 times 100, right here, count the number of zeros. 1, 2, 3, 4. That's actually going to give us 10,000. 10,000 has 1, 2, 3, 4 zeros. And then we still have this 100 over here that we need to multiply by. 10,000 times 100. Again, let's count our zeros. We have 1, 2, 3, 4, 5, 6 zeros here. So that's going to give us 1 million. So 10 to the 6th power is equal to 1 million. Okay, moving on to the back side. Now we're going to look at what are square roots and also what are called perfect squares. So when you see numbers like 9, 16, and 25, we call those kinds of numbers perfect squares. Perfect squares. And we call them perfect squares because those types of numbers are actually squares of whole numbers. So for instance, 3 squared gives you 9. 4 squared gives you 16. 5 squared gives you 25. Those types of numbers are called perfect squares. We're actually going to go through now, we're going to list the first 25 perfect squares so we can recognize when we have those kinds of numbers. So anytime you hear me say 1 squared or 2 squared or 3 squared, that just means that number times itself, or that number to the second power. Okay, so right here we have 1 to the second power, which we know from our what we just talked about with exponents. 1 to the second power means 1 times itself 2 times, so 1 times 1. And 1 times 1 is, of course, 1. So 1 is the first perfect square. 2 to the second power means 2 times 2, which gives us 4. 3 to the second power means 3 times 3, which gives us 9. So there's 9, our first perfect, the perfect square that I talked about up here in this list. 4 to the second power means 4 times 4, which is 16. 5 to the second power means 5 times 5, which is 25. I can also call this, instead of 6 to the second power, I can say 6 squared. So anytime I say you're squaring a number, it just means to the second power. So 6 times 6 is 36. 7 squared means 7 times 7, so 49. 8 squared means 8 times 8, which is 64. And then we have 9 squared, which is 81. 10 squared is 100. 11 squared is 121. 12 squared is 144. And then over here on the right side, so the left side of the list are the numbers that you should, if you know all of your times tables through the 12s, okay, you should be able to get those rather quickly. The rest of this list are multiplication facts you probably don't have memorized, so you'll just have to trust me as we go through this list. 13 squared is 169. 14 squared is 196. 15 squared is 225. 16 squared is 256. 17 squared is 289. 18 squared is 324. 19 squared is 361. 20 squared, think about what that would be for a moment. 20 squared gives you 400. And then a few more we're going to look at. 21 squared is 441. 22 squared is 484. 23 squared is 529. 24 squared is 576. And 25 squared is 625. So the reason we're listing all those numbers out is I want you to become comfortable with seeing those numbers, especially these first, I'd say, 15 or so, but really all of them, and recognize that whenever you see these numbers, okay, especially when you see them underneath the square root sign, which we'll talk about in just a second, you can see that these numbers here are perfect squares. Okay, you can take a whole number times itself and always get numbers from this list. Okay, so now moving on to the bottom here. The whole number base that we use to find the perfect square is what we call the square root of that number. So for example, because 7 squared is 49, we say that 7 is the square root of 49. The symbol for square root is this. It kind of looks like a slanted long division sign. Okay, so anytime you see this symbol, you would say the square root of. So going to this next page here, we're going to simplify each of these square roots using that list we just made above. So number 5, we read this as the square root of 144. And so to find that, you just have to ask yourself, what whole number times itself gives us 144? Well, on this list, 12 squared is equal to 144. So we know the square root of 144 is 12. For number 6, we have the square root of 289. If we go back to our list, we see that 17 squared gave us 289. So the square root of 289 is 17. Lastly, number 7, we have the square root of 576. From our list, we can see that 24 squared is 576. So the square root of 576 is 24. So that works all nice and neat when the number underneath the square root sign is a perfect square, okay, when it's a number from that list that we made, okay? But not all numbers are perfect squares, okay? So for instance, if I ask you to find the square root of 30, which I'm going to down here in example 8, okay, there is not a whole number times itself that would give you 30. So that's why calculators also help when we're trying to estimate the square root of a number. Okay, calculators have a square root button when you need to quickly approximate the square root of a number. But in this class, we're not going to use calculators, so you need to have another method to estimate square roots of not perfect squares. And so we're going to do that here in example 8. We're going to estimate the square root of 30 without using a calculator. So the first step to estimating a non-perfect square root, like the square root of 30, is to find the two perfect squares that 30 fits in between. So if you go back up to your list, find the two numbers that 30 is in between. What two numbers written in blue does 30 fit between? Well, if I go down this list, I see I have a 25 here and a 36 here. We know that 30 is somewhere in between 25 and 36. So that means that the square root of 30 is going to be somewhere in between the square root of 36 and the square root of 25. Now, 30, is it closer to 25 or is it closer to 36? Well, 25 is 5 away from 30, whereas 30 is 6 away from 36. So 30 is just slightly closer to 25 than it is 36. Okay, that's step 2, is to figure out which of these numbers 30 is closer to. Okay. Step 3 is to find the square root of the number that 30 is closer to. Well, we know the square root of 25 is 5. The square root of 36 was 6, but because 30 is closer to 25, we're going to say that the square root of 30 is approximately, it's not exactly, but it's approximately, and that's what this little squiggly equal sign means, approximately 5. Okay, so by finding what two perfect squares 30 lies between, we can say that the square root of 30 is approximately 5. So now we'll do that for these last 3 square roots here. We have the square root of 45. So we know the square root of 45 is between what two perfect squares? Well, take a look at your list. You see we have 36 and then 49. So 36 and 49 are the two perfect squares that 45 is between. The square root of 36 is 6, and the square root of 49 is 7. So 45 is somewhere between 6 or 7. And when we approximate this, 45 is closer to 49 than it is 36. So we'll say that the square root of 45 is approximately 7. Okay, what I want you to do now is I want you to go ahead and click pause on the video, and then I want you to try examples 10 and 11 on your own, the same way we did number 8 and number 9. Once you've done those on your own, click play, and then you'll be able to check your answer. Okay, so let's look at what you came up with for 10 and 11. So number 10, you had the square root of 78, and the square root of 78 is between the two perfect squares of 64, square root of 64, and the square root of 81. So the square root of 64 is 8, and the square root of 81 is 9. 78 is closer to 81 than it is 64, so we're going to say that the square root of 78 is approximately 9. Okay, again, not exactly, but it's closer to 9 than it would be to 8. And then number 11, square root of 500, well, that's between the perfect squares of 484 and 529. So the square roots of those numbers are 22 and 23. 500 is 16 away from 484. It's 29 away from 529. So we're closer on this one to the square root of 484, which is 22. So we're saying approximately 22. Okay, so that's it for this video. As I said at the beginning, if you had any questions over this, make sure you jot those down on the notes, and then you can ask me those questions the next time I see you in class. And until that time, I want you to have a nice day, because you're all wonderful people. Take care.